Okay, good afternoon. Today we're going to wrap up rectifiers. We'll look at example two, maybe one and a half examples, and then we'll introduce Zener diodes. Okay. So, okay, I believe we stopped here last time, and we were in a little bit of rush trying to get this done. So let's just quickly go over this. So in LT Spice, it's possible to simulate, a lot of our electric circuits and electronic circuits. The purpose of a computer simulation is obviously, of course, to generate some answers so we can have theoretical calculations that we perform manually. Then we have computer simulations, which is a calculator in software. And then, of course, we have our experimental actual values. So in LT Spice, we can use, there are multiple diodes that are available. You can use 1N4000 series, 1N914, simulate a half-wave rectifier with or without a capacitor. And these are the output waveforms, right? This is without a capacitor. So this is what was known as pulsating DC output. And there's a small voltage drop right here that accounts for the diode turn on voltage, right? So V out is going to be V in minus the diode turn on voltage. For our case, it's typically 0.6. You refer to the book. In LT Spice, if you're running a simulation, you can specify diode parameters. So if you just choose 1N914, it'll automatically take the values for 1N914. If you manually type in the text, then you can select any diode that you want. Okay. If you're creating a circuit graphically, you're limited to only the components that LT Spice has. Okay. All right. From there, we looked at using two half-wave rectifiers to create a dual DC supply, meaning a plus minus DC supply, something that we used in the op-amp labs for the, what was it? 2 or 3, I believe we created a dual power supply. So the diode for the first one, positive, is facing towards the right. That's your resistor, load resistor. And then the same line goes to another diode that faces to the left. Now, the thing that creates this dual supply is the same common terminal that we use for ground or for reference. So if you notice, all of these terminals where you see this ground symbol in LT Spice, a triangle, it's basically this symbol. That's the common reference point for everything, right? Simply switching a diode around would not do anything except it'll just rectify the negative half cycle. But the diode is flipped around, plus we are using the same reference. And when that happens, the capacitor for the first, C1, which is right here, positive half, gets charged and you have a positive output. In the negative half cycle, because the diode is flipped, diode D2 conducts, capacitor charges C2, and C2 output results in a negative. So D2 and C2 act as a negative peak detector. And that's how we obtain a dual power supply using one single source. Okay. So again, this is something you can simulate in LT Spice. And if you're interested, you could do this in the lab also. You have two diodes in your lab kit. You have capacitors, you have resistors. You could easily perform this experiment in the lab. Okay. All right. So filter capacitors. So how the purpose of the capacitor is to eliminate the ripple or eliminate. Sorry, let me turn this off. So depending on our requirements, we would want the ripple to be almost non-existent or at least very, very small, right? No circuit is ideal, no capacitor is ideal. So depending on the size of the capacitor, it's going to affect circuit operation. So normally we would think we can just attach a large capacitor at the output, like 1,000 microfarads or 10,000 microfarads. So typically I've seen 10,000 microfarad capacitors connected to the output of a bridge rectifier circuit. So with such a large capacitance, the discharge will be very, very slow. So the ripple voltage, VR, will be very, very small. So the equation that relates the capacitor to the ripple voltage is given right here for both half wave and full wave rectifier. So if we were designing a system for a particular application, and we were to choose a value of a capacitor, of course, is going to be indirectly proportional to VR, or VR is inversely proportional to capacitor, right? Larger the capacitor, smaller the ripple voltage. T is the time period of the waveform. So one single time period. T is also the inverse of frequency. So 1 over F, or F is equal to 1 over T. And then IL is the load current, which of course is a critical factor in those equations. Depending on our load and depending on the load current requirements of the application, capacitance value can be designed. Okay. Now, all right, any questions thus far? Okay. I want to go over something that you may have come across in, well, you might have studied in 115, E115, or maybe 215. Peak values, magnitudes, RMS values, and DC or average values. They'll cover that in 215. Okay, some nods. Okay. All right. So we've been talking about sine waves and rectification of a sine wave into a DC waveform. So let's talk about. So I'm gonna refresh everybody's memory a little bit. Time is always on the x-axis. The quantity that we are, quantity is always on the y-axis. So it would be voltage or current or power. This would be plus, this would be minus. Current or, well, power is never negative, but let's just say voltage or current, okay? And then we have a sine wave, sinusoidal waveform. It has three elements. One is phase. Phase difference is the moment in time where it crosses x is equal to 0. Sorry, y is equal to 0. And that's given right here. So this waveform begins at 0. So phase shift is 0. Then we have this. That is known as the peak value of the waveform. Okay, peak value of the waveform. And correspondingly, the waveform is symmetrical, so we have a negative peak. Now, if you recall lab 3, when we were performing the amplifier has a DC component in it. So there's a positive DC component to that output, so it shifts the waveform up. Nevertheless, it is still referred to as a peak-to-peak waveform, like a positive and a negative peak. Okay, even if the waveform is completely above 0, that one is still referred to as the negative peak. All right, so we have VP. VP stands for peak or magnitude or amplitude. In higher level E classes, we often use the term known as amplitude. Amplitude means the exact same thing as peak values. It's basically the quantity on the y-axis. Sometimes you would see some authors like to use M for the subscript. So VP, IP, IM, or VM. So if you come across something like that, again, it means the peak value of the waveform. Then you have P dash P. That is peak to peak. So peak to peak waveform is it's twice VP. And sinusoidal waveforms are represented as a time varying signal as V of t, VP, sine of omega t plus or minus theta. Okay. Trigonometric identities, either sine or cosine, sine omega t or cos omega t. T is the variable because we are plotting the value of the quantity. We are plotting the voltage as a function of time. So T is the variable. Omega is the angular frequency or the angular velocity equals to 2 pi f. F is the frequency in hertz. Omega is 2 pi f, and f, of course, is inverse of time, 1 over t, the time period. Okay. So three quantities, Vp sine omega t. Omega is the frequency. Vp is the peak value, meaning on the y-axis, and the theta angle is the phase difference, the phase shift from the zero value. You won't worry about all of that because I'm assuming you've covered all of that in 15. Anyway, so the way this applies to us is, if you take the average value of this waveform, what do you obtain? 0, right? Yet, when you apply AC signal, where you send an AC signal to a resistor, energy is supplied, power is supplied to that resistor, right? So how do we represent that power? And so you have the term RMS, the root mean square, right? So equation for power is V square or R, square of the voltage. So if we wish to describe the value of the AC waveform, that would be equivalent to a DC waveform that produces the same energy. That value is known as the RMS value of that waveform. You have a resistor R. If you connect resistor R to a DC supply, it will receive some energy. If you connect an AC, it will still receive some energy. So the value of the AC waveform that generates the same energy in that resistor, delivers the same energy, same power in that resistor as the DC value, is the RMS value of the waveform. Obviously, we cannot take the average directly. So decided to take the square of the waveform and then take the average. Average is basically summing up everything under the curve. So integrate between one time period and then divide by the time period. So you get the average. And because we took a square at the beginning, now we take the square root. And hence the name RMS, root mean square. It is the square root of the mean of the square of the waveform. That's where the name comes from. So if you have any kind of waveform, and this applies to all kinds of AC waveforms, not just sinusoidal. You can have a square wave, triangular wave, sawed ramp. Every waveform has an RMS value. Okay. Now this is important for rectifier circuits because in rectifier circuits we have an output that is going to be, let me then output will have an equivalent DC waveform sorry, DC value, but the DC value is not the same as the RMS value. Okay. So again, VRMS or IRMS is the root of the mean of the square of the waveform or the value. And for sinusoidal waveforms, what is the relationship? Anyone remember? There's a derivation. I don't know if you all did that derivation or not. I believe the book does have one, so you can look up and refresh your memory. But this boils down to √2 times the RMS value of the sinusoidal waveform. So if your waveform is described in a peak-to-peak or peak value, you can determine the RMS value simply by multiplying by √2, 1.414. All right, any questions so far? So at this point, I ask students, what is the value of the power outlet, the voltage of the power outlet? 110 to 120 volts. Let's say 120 volts. Is that peak or is that RMS? One student says RMS, another student nods. Nobody for peak? Peak is all by itself. Y'all confident? Yeah, you should be. It is RMS. Unless explicitly stated, all values are always in RMS. All meters, everything that you measure, all quantities are always in RMS. If you take a multimeter, for example, the ones that we use in the lab, and you connect it to your circuit and you measure 5 volts, that is 5 volts RMS. Okay, it is not peak to peak. The only way we are observing peak to peak in the lab is by observing it on the oscilloscope. Oscilloscope can provide us peak to peak values. These nice new digital oscilloscopes also give us automatic calculations of RMS values. So unless explicitly stated, all values will always be in RMS. So to determine the peak to peak values of our power outlets, you have to take 120 times 2, 240, and 240 times √2. Sorry, √2 times VRMS, so √2 times 120 times 2. So 2 √2 times 120. That's a swing of over 350 volts. Okay, swing of 350 volts. So the reason peak values are important is because electricians and engineers need to know what is the maximum value of the voltage or current that is flowing through your electric lines. Okay, the effective value is RMS, but that voltage or current is still reaching that peak value. And obviously it's very fast, it's 60 times in 1 second, but that peak value is very important. That's why we use both conventions, peak to peak and RMS. Yes. That's just peak to peak, because that does not have I mean, it came from the sinusoidal waveform, but does not have a defined name for it. It's just AC. So the question being asked is for ripple, for a ripple voltage, how do we measure it or how do we define it? We define it either in peak to peak, or RMS. So ripple voltage, VR, can be defined in both peak to peak, VR peak to peak, or VR RMS. If it's not defined as peak to peak, then you can safely assume RMS. Okay. So in the lab, when you performed experiment 3, you applied 100 millivolts peak to peak from the function generator, and we were measuring RMS, and we can of course measure peak to peak also at the same time. So you observed it was about 33, 35 millivolts, which is about right. So then if your sine wave input is sinusoidal, what about the rectified pulsating DC, right? Pulsating DC looks like this. So what? So here we have two values. We have a DC value for the waveform. I'm just going to make an approximate mark. And there will be an RMS value of the waveform. Okay, DC and RMS value. The RMS value is straightforward. It's actually not there. VRMS is 0.707 times VP, peak value of the waveform. The DC value is determined simply by averaging out the entire waveform. So we integrate the waveform from 0 to t, and that gives us the DC value. So VDC, or let me say more accurately, V out DC. V out DC is 1 over T VO of T dt. Okay. You integrate the waveform over one time period, and that gives you, and you average it out, that gives you the DC value. And that turns out to be for a sinusoidal waveform, turns out to be 0.318 for a half-wave rectifier and 0.636 or 0.637 for a full wave. And that's where this equation comes from. So V out DC is the average of the entire waveform over one time period. And for a sinusoidal half-wave rectifier, turns out there's VP over pi. Because a half-wave rectifier, if you plot in radians, let's do it this way. That's the actual time period for a half-wave rectifier. For a full wave, the frequency is doubled. Right. Frequency is doubled. So from the original frequency for a full wave rectifier, it's 2 times VP over pi. Okay, times VP over pi. VP over pi comes out to be 0.318 VP. And this one is approximately 0.637 times VP. And the RMS value is 0.707 times VP. All of these values are important, but the most important would be the RMS and the peak values. Okay. All right, let's take a pause. Let me know if you have any questions. Yes. So the question being asked is, would the RMS value for a sine wave with both positive and negative, would it be equal to the rectified output? full wave rectified output? It's a good question. I never thought about it. But it seems you average it out, you take the RMS, it should be the same. Yeah. Where's the waveform, V of t? The time period would be different. Because for a full wave rectifiers, the time period, the frequency is doubled. So if you apply 60 hertz signal to a half wave rectifier, you obtain a 60 hertz frequency output. If you apply 60 hertz to a full wave rectifier, the output is now 120 hertz. It's doubled because the negative half cycle is also being rectified. Right there. So it would not be the same. That was my point. The frequency would be different, so you'd be averaging it out over one cycle versus two for a sine wave. One other thing, this DC value of this rectified waveform or the waveform is also known as the average value. So if you read the words average value of the waveform, what it means is that DC value of the waveform. To make it even more confusing, this DC is not the same as the RMS value. So is not the same as RMS. Okay. And the reason we describe RMS is again because power is squared of the voltage. If you take any two numbers, the average of the squares of those two numbers is not the same as the square of the average of those two numbers. Let's take, for example, 3 and 5. The average of these two numbers is 4. Square of the average is 16. Now, if you take the same numbers and square, now the sum or the average of these two numbers, 34 or square root of 34, is larger than 4. Okay, it's larger than 4. Sorry, not 16. It's larger than 4. So average of the squares is not the same as the square of the average. There's a lot to think about or get your head wrapped around it, but you can review this outside of class and let me know if you have any questions, okay? But anyway, there's a purpose for the RMS values. That's what I'm trying to get at. All right, so let's go to the example problem. All other equations apply exactly as they are. So if you're taking RMS values, you work in RMS, you can apply Ohm's law, KCL, KVL, everything applies exactly the same. If you're using peak values, again, Ohm's law, KVL, KCL, everything applies exactly as it is. Okay, no difference in the laws. All right, so first example has to do with half-wave rectifier. If we have a half-wave rectifier, one diode standard pointing when we refer to half-wave rectifier, we always mean this circuit, right? There could be 4 different kinds of half-wave rectifier depending on the configuration of the diode, whether it's connected on the negative side or the positive side, right? But simply stated, half-wave rectifier would always mean this kind of circuit. So you have this diode, you have V in of t, time varying waveform. You have RL load resistor, voltage across that load resistor, VRL. And then you have the diode voltage drop. Our book uses V gamma to indicate the diode voltage drop. So we'll use the offset diode model. 0.6 volts. Okay, 0.6 volts. V in RMS is given as 20 volts, and RL value is given as 50 ohms. Question being asked is determine the value of the peak, determine the peak value of the current, also determine the RMS value of the current. Okay. The current, of course, because it's a series circuit, is going to remain the same. The same current is shared, the power supply, the diode, and the load resistance. Okay. All right. So let's first find the peak value of the voltage, of the input voltage, right? We're asked to determine the RMS value and the peak values. We can start either with the RMS as it is, or we can start with the peak. I'm just going to show you the peak, even though it's not required. So how to solve this? Let's say find the peak value from the RMS. So V in or VP is √2 times V in, which is in RMS. So VP is √2 times 20. Therefore, the peak value of the voltage is 28.2842. Okay, 28.2842. All right, once we have VP, we can apply Ohm's law. We are asked to find the current. We have voltage, we have resistance, we can apply Ohm's law. Okay. So from Ohm's law, we can write IP is VP over RL. Two 842 divided by 50. Someone perform the calculation. What do you get? We have not yet. Not yet. So the question being asked is it counting, is it accounting for the diode forward voltage drop, the offset voltage of 0.6 volts? So not yet. Yeah, it's a sine wave. Yeah. So sometimes, not sometimes, most of the times, DC and AC values are both represented just as plus minus. So it represents both AC waveforms and DC waveforms. But typically, if you're talking about rectifier circuits, it's always like sine waves. Yes. Yes. For a rectifier circuit, yes. Yeah. So if it's not given in the problem, then you can safely assume it's a sine wave. Okay. What value of IP did we get? All right. That's close to what I have. That's what I have. 0.565685. I just felt like taking 6 decimal places. Usually I take 3 or 4. All right, so then what is the RMS value? We saw the equation. We saw the equation of the voltage, but it remains the same for the current also. So how much do we have for the RMS value? How much is this? Which one? Load isn't on? RMS would be divided. So the question being asked is, would the RMS value be divided by 2? No, because we are not talking about peak to peak values. We're simply talking about peak values. So the mathematical equation simply applies as VP. When the current or when the voltage is negative, there'll be no current, which will affect RMS. So yes, peak value stays the same. That's the top. So this is without the diode voltage drop. So if you're applying 28.28 volts in there, your output peak value will also be 28.48 volts. But then the RMS value for that voltage will still be √2 times or divided by √2. RMS times √2 is, it's always in the positive way, yes. Negative. So that's where the DC comes from. That's why we have 2 different notations. So if I'm understanding you correctly, you're saying when we find the DC or the average value of the waveform, we are dividing by 2 because we have accounting for the 1/2 cycle. So how come we don't do that for the RMS? And that's why we are using two different things. For RMS, we do not divide by √2 because we are not describing the waveform as peak to peak. In this case, the peak value of the waveform is the peak to peak value. So for a half-wave rectifier, the waveform is this. So the peak value of the waveform is also the peak to peak value. That's why. Kind of like the ripple voltage. Ripple voltage question was asked earlier. You or someone else had asked about it. And we said, even though the ripple voltage it's not like a sinusoidal waveform, it's still referred to as peak to peak because it's like the maximum value to the minimum value. So that's a good question. So if it's not a full sine wave, can we still use this equation? Yes, it still works. The answer is yes, it works. So what was the answer for I RMS? That's it. All right, so let's now find the average value. Average value would be IP over pi. So what does that come out to be? Anyone? Just 0.18? Is it 3.6 or 6.3? 3.6? I had 6.3, probably I read it wrong. You got 6.3 too? Yeah. So you're making me doubt myself. You're confusing me. That's fine. So 0.18 amps. The reason I'm going like 5, 6 decimal places is because here we are doing amps, but typically many of the circuits we deal with would be in milliamps or even microamps. So if you look at this number, 0.565685, that is 565 milliamps, right? 565.68 milliamps. So that's what. Yes. 0.707 times the peak value. So RMS is equal to, sorry, V peak, peak values for sinusoidal waveforms is √2 times the RMS value. Yeah, so you take √2 on the other side, divide by √2. Now, if you were to take the diode voltage drop into account, then we got V in or V here, we have VRL over here, and the diode voltage drop V gamma would be here. So now if you want to find VRL, we cannot use VP directly. So VRL would be V in minus gamma. Okay. V in minus V gamma. Since we already given the RMS value, we can just directly use that. So it'll be 20 volts minus 0.6 volts. So now VRL is 19.4. And you can perform the rest of the calculation using the exact same equations. So ideal diode model analysis and offset diode model analysis. The values would not be too far off. So that's why ideal diode is still used for many analysis techniques. C153. All right, let's see. I want to please introduce Zener diode in the time we have left. Okay, Zener diodes. We referred to this a bit when we were looking into fundamentals of semiconductors, right? You have a p-n junction diode. When you create a p and n junction without applying any bias, when they come into contact, holes and electrons cross over, they recombine, and there's a region that is created in the middle that is known as the depletion region because it is devoid or depleted of all charge carriers. If you apply an external voltage to the p-n junction, if you apply positive polarity to the p-type and negative to the n-type, we say it's being forward bias. If you apply negative to the p-type and positive to the n-type material, we say that p-n junction device is being reverse bias. And when it's reverse bias, it's completely off. No current can flow through except for a small amount of minority carriers. So I believe we covered conduction in the reverse bias due to minority carriers, two effects, Zener and an avalanche effect. Do you all recall, remember? So in the reverse bias, you have minority carriers that are able to pass through the junction, right? The junction keeps on increasing until a point is reached when the electric field causes new free charge carriers to be generated. So you have a reverse bias junction. Let's say this is the original depletion region between the P and N type material. Negative and positive. right? You have holes here and negative electrons here. They're attracted away from the junction. So the junction or the junction width increases. Depletion region increases. Okay. Now in Zener diodes, if you dope these semiconductor materials heavily, there is an excess of charge carriers that are present. Okay. So even though it's in reverse bias, when there are excess charge carriers present in a very thin junction, again, that's a factor of the design and the doping profile, these carriers are able to cross over the junction because they are minority carriers. Okay. So Zener effect occurs for voltages less than 5.6 volts. And above 5.6 volts, the electric field that is applied due to the external voltage is going to rip out electrons from the atoms. Remember, intrinsically generated charge carriers were due to thermal energy. Now we are applying an external electric field. Because the device is very small, the junction is very thin and small, the external field or the field density is quite large. And because of this, electrons are pulled, or let's say they acquire enough energy from the external applied voltage that they now move out of their lattice structure and are able to conduct. And as soon as they move out, if they are within the depletion region, they are immediately attracted. So if they are within this region right here, the excess charge carriers generated, let me see. Generated due to, let's say, Vs in reverse bias. These electrons, if they're within that, they are minority carriers. There are holes on the other side. They are swept away. They come under the influence of the external field, and they pass through the junction. Each electron that is created this way is accelerated across the junction. It may collide with other atoms, thus dislodging more electrons. Those electrons will dislodge further more electrons, and it creates a cascading or avalanche effect. And that's how we have a large current flowing in the reverse direction. One of the properties of this reverse bias action is that the voltage across the device remains very constant. So the voltage remains constant while the current keeps on increasing. So this is one of the most important properties of this kind of diode. So the diodes that are specially formulated to operate in reverse bias are known as Zener diodes. They're specially formulated to operate only in reverse bias. The special property is that in reverse bias, once the junction breakdown occurs, that breakdown is on purpose. Okay, the breakdown is on purpose. It does not mean the diode is getting destroyed. It's just breaking down. So even a regular diode, you can apply a high enough voltage that will break down. But even after breakdown, the diode will still continue to function. So Zener diodes are specifically designed and formulated to work in breakdown. 159. Breakdown region. Voltage is constant or near constant. And the excess energy results in an increased current flowing through the diode. Okay, so the Zener diode can be modeled in the forward branch. It can be modeled as two diodes in parallel, both facing in the opposite direction. When you're forward bias, In the forward bias, the diode acts like a normal diode with a diode series resistance and the diode voltage drop. When you apply a reverse bias, again, behaves like a regular diode, and it will have some resistance. That resistance is known as the Zener resistance RZ. And then more importantly, the voltage at which breakdown occurs is known as the Zener voltage. And when we purchase diodes, or we are designing a system application using Zener diodes, we look at the specs. The specs will state VZ. That is the voltage that is required to turn on the diode in reverse bias. And there is also a power rating associated with it, because as you increase the voltage to the device, you're sending more power, you're sending more energy. Power is the product of voltage and current. If the voltage remains the same, but the power increases, then the current has to increase. So the Zener diode, current increases, voltage remains constant, and PZ and VZ be part of the diode spec. Circuit symbol is exactly the same as a diode, except the cathode has whiskers, like this. And that's a Zener diode, and the characteristics are shown here. Forward bias, it behaves like a normal diode. We are out of time, so if you have to leave, you can leave. So forward bias, it behaves like a normal diode. In reverse bias, there is a small saturation current. Obviously, this is exaggerated because the saturation current is typically nanoamps, picoamps, and femtoamps. And then once breakdown occurs, right there, this remains near constant. The voltage remains near constant. And the current increases. And that's why we are able to use a Zener diode as a voltage regulator, okay, which we'll see next week. So we'll end class here today. There's homework that is posted on the website, the short homework. It should not take you long. There's extra credit reading that is also posted on there. And then we'll have quiz as usual on Monday. Quiz will be based on the topics that we have covered this week. Okay. All right. Have a good weekend, and I'll see you all on Monday.